I'd like to now introduce our second speaker, Ryan Walker. Ryan is from Easton, Pennsylvania. He studied mathematics at Haverford College and then did a PhD in atmosphere ocean science at New York University. He began his scientific career as a glaciologist, studying the Antarctic ice sheet, working at Penn State and NASA Goddard. He has done field work on the Southern Ocean and in Antarctica. In 2020, Ryan switched fields by joining the Lunar Reconnaissance Orbiter team, where he supports the Lunar Orbiter Laser Altimeter instrument. And of course, he has not yet done any field work for this job. When not pondering the moon, Ryan enjoys playing the guitar and cheering on his Phillies and Eagles. So, Ryan, take it away.
Okay, so the last crewed landing on the moon was Apollo 17 back in 1972. And one of the things that was noteworthy about that was that it was the first and only mission to actually bring a scientist. So we're talking about field work. That's Dr. Harrison Smith there taking a sample from that huge rock. And he had actually been the field geologist trainer for the astronauts on some of the previous missions. So on the last one, they finally let him go up. You can say, actually, Jack is still heavily involved in the research community to this day. I've met him at a conference, and he is about the nicest, friendliest you could ever hope to meet. So there was a great legacy from Apollo, but there wasn't any lasting presence on the moon. So while some of you will remember this well, nobody's been on the moon in my lifetime. And so when they made the first landing, so this is Apollo 11, they were working from, much more limited information. So here, these are a couple of examples of the kinds of maps that they had for planning the landing. So this is based on the Ranger 8 and Lunar Orbiter 2 spacecraft, and then also the Apollo 10 mission, which orbited the moon and tested the landing module, also got some images of this site. So they had reasonably good image of where they intended to land. But then, not everything goes right. They overshot by a mile or two. And next thing you know, there's a field full of boulders the size of Volkswagens. So the good thing is Neil Armstrong was an amazing pilot. He saved it, obviously, but they landed with less than 30 seconds of fuel left before they would have had to fire the rocket and wave off the landing. So the plan in the next couple years is for the NASA Artemis program to land in the South Polar region. That's because we do expect that that's the area that has the most resources, like water, hopefully, that would allow a lunar base and a sustained presence. But, this is going to be more difficult. Most of the Apollo missions landed on the lunar Maria, where it's a nice flat lava plain, so that should make it easier. Here, landing in the South Pole area, you have more complicated topography and more challenging lighting conditions. And also you're trying to land a much bigger ship here. So what do you do if you need that? Well, you launch a lunar reconnaissance orbiter. And so that launched back in 2009 on a one-year mission. And so I joined in year 11 of the one-year mission. Actually, because I was in glaciology, even though I love this kind of stuff, somehow I didn't know this existed until I got contacted to work on it. And we actually just now got the go-ahead for 3 more years. So by a long shot, LRO has collected more data than all other planetary missions combined. And part of that is, well, if you're going to send a spacecraft up, basically we send in everything. So a couple cameras, an altimeter to get the topography, radar, ultraviolet sensing, thermal infrared, and a neutron detector, and this and a radiation sensor that gives a pretty good idea of obviously the weather and radiation environment around the moon, which is also a significant challenge for astronauts to face. So this is what LRO looked like in the clean rooms at Goddard when it was sort of finished up being assembled, and all of the different instruments are obviously labeled in the photo on the left. I just want to note one thing that is useful about this, and you can kind of tell, is that LROC, the camera, and Lola, the altimeter, point exactly the same. And so that's really good for getting an idea of what the ground's like, because you combine the photos and the laser sensing, and they're simultaneously right on the same spot. And then just to get an idea of the scale of the thing, here LRO is on a tilt test, and you can see the people standing on the ground. So it is a decently big vehicle. And so now this is going back to, so this is where Apollo 11 landed. I tried to center this, so the blue dot is, sort of our best estimate, is sort of the best I could do on this map to put it there. And you can even, I believe some of the white around there is even the effect of the landing rocket. But when you're looking at this, compared to what they had in the 60s and 70s, so this imagery, this is at a 0.5 meter resolution. And when you look on the right, that's the same image, and I've just sort of, semi-transparently overlaid one of the contour maps of the elevation. So this is a lot better information than was available at the time. So this is a mosaic put together of many photos that LROC has taken globally around the moon. So the thing that perhaps stands out the most, besides getting to look at the far side of the moon, is that, all of the Maria, just about all of the Maria, your ancient lava plains, are on the near side. There are very few on the far side. And whether that goes to impacts or some kind of asymmetry when the moon was cooling, that's still an active area of research. We don't really know that very well. But now if we want to take a close-up now, this is a relatively recently formed crater. I think this might be one of the ones that was actually formed from an impact while LRO was in orbit. And you can see, like, this whole image is about 3 kilometers, about 2 miles wide. And if you can look here, I mean, it's down to you, right? I mean, you look around the edges here, you're looking at individual rocks that got ejected during that impact. Yeah, there's still a lot of so are these meteors still striking the moon? Yeah, pretty constantly, not as much as earlier in the solar system, like anywhere from like 3.5 to 4 billion years ago. There was just a lot more stuff floating around and being consolidated. So a lot of the impacts, pretty much all of the major impacts, are pretty old, and there's less stuff going around, kind of for the asteroid belt to hit the moon, but it still happens. There was, I think, a 600 plus meter crater, occurred while LRO was in orbit. We also got images of, and then also, it's down to, there are things as small as dust particles frequently coming in and smacking into the moon. So there are lunar rocks then brought back where they call them zap pits, because that's kind of what they look like, where there are little craters in the rocks that are smaller than the diameter of a human hair. So there's all kinds of stuff coming in. Hasn't been anything massive recently, but we are still seeing this. And another cool thing to do with the camera for supportive landings is, photograph missions when they have landed. So this is the Firefly Blue Ghost mission, which landed successfully in March of this year, which made it the first spacecraft flown by a private company to successfully land on the moon. And this was a contract to NASA. So you can see there's a larger image, the broader image, and then blown up a bit. And you can even see in that, so you can sort of see the shadow of the lander in the center. But then, there's that white bit of the fan around there. And that's the result of the landing jet coming down, because the dust right on the surface tends to be dark because of getting smacked with radiation and all these little meteoroids. So when the landing jet comes down, it blows a lot of that. Say up in the air, there's no air, but it blows it up off the surface, and you wind up with this lighter sort of thing. And another fun thing on this is actually one of the things I don't know where it is exactly on this photo, is they do have what's called a retroreflector, which is just a cube of mirrors that's designed for ranging by lasers. If you can actually hit it, then you can get a super precise location, which is great for navigation. And the LOA instrument, which has 2 lasers, has recently been doing a pretty good job of, even though it wasn't really in the mission design, our engineers have managed to hit the retroreflector on this a few times in the last month or so. No, that's with it on the ground. That one's not going back. No, that one's staying there. And so switching over to the topography, this is what's gathered by a lunar orbiter laser altimeter, or LOLA, which is the instrument I work on. So you see again on the near side, a lot of those blue and light green areas there. Those are where the Maria are, again, the lava plains, which makes sense, right? The lava goes downhill, fills in the middle of the highlands around it. Nice and flat. But then there have been more big impacts as, some high mountains and such, on the far side of the moon that we don't see. And then also on the far side near the South Pole, obviously, there's this huge blue area there. And that's the South Pole Aitken Basin, which resulted from, I guess what we would call in scientific terms, a ginormous impact. And so this is a very interesting area potentially to study, because a huge impact. It's possible, that, the ancient material from the moon's mantle got blown up to the surface there. And so all of the landing sites that are being looked at for Artemis are in that general region. So another fun thing about this is that we actually know the surface topography of the moon better than any planetary body in the universe. And that includes Earth, because, well, the moon notably not having any oceans, we can image the whole thing. So, we have, so we actually do have better data all around on the moon than we do on the Earth because of the oceans. And so this is, sorry, kind of a nice, fancy topographic map, in that South Pole area. It was made by LOA data. I think these are around 100-meter contours here, but it does come out with, quite a lot of detail. And so if this will play, this is a quick visualization. Mark might have seen this before because this is from the Science Visualization Studio. And so this is simulating. Is the volume on? Oops. Okay, so since for some reason the volume is not working here, let me run that back quick. So this is showing. So this is LRO is flying over Amundsen crater near the South Pole. And this is showing what Lola is doing. So that's the image of the simulation of the laser spots coming down. So this is on the orbit height. This is maybe 50 meters wide at the time. And it's taking those 5 spots like a dice pattern at the same time. So by doing that, you get distances, but you can also get the slope because you've got those 5 spots at the same time. And as you probably saw when it paused there, I don't know why, but from the beginning of the mission, when they show those spots in the area that's detected around them, for some reason they always draw them looking like olives. If you saw there was the red spots and this dark green around this, I don't really know why they have been doing it that way, but that's what it looks like when Lola sweeps, one ground track across a crater here. And of course, there are many, many, many ground tracks put together in order to derive these maps. And so there's just even more of a close-up on Amundsen crater. So what we showed in the simulation again was one of the many runs that went over this crater and contributed to having this, really very nice topography there. But the next thing, though, is it's not just challenging to land, but the idea with the Artemis program is to wind up with a sustained presence, to wind up with a lunar base, with lunar bases, and even eventually as a staging area to go to Mars. So if you're going to do that, you're going to need to get quite a bit of resources to work with. And one of the most important ones is water. And the likely presence of water near the South Pole is one of the main motivations for why all of the Artemis target sites are down in that area.
As you watch the moon over the course of a month, you'll notice that different features are illuminated by the sun at different times. However, there are some parts of the moon that never see sunlight. These areas are called permanently shadowed regions, and they appear dark because, unlike on the Earth, the axis of the moon is nearly perpendicular to the direction of the sun's light. The result is that the bottoms of certain craters, like here at the moon's south pole, are never pointed toward the sun, with some remaining dark for over 2 billion years. However, thanks to new data from NASA's Lunar Reconnaissance orbiter, we can now see into these dark craters in incredible detail. Seeing the shape of the crater is important, and LRO has used its Lola instrument to make the best yet topographical maps of these craters by reflecting lasers off the lunar surface. This has allowed us to see the shapes of the crater's interiors from any angle, and by making 3D models, we can light up the crater floors as if we had a giant flashlight. And although the sun never illuminates these craters, other stars still cast a faint light into the permanent shadows. LRO's LAMP instrument can actually measure this light, giving us yet another view of this unique region on the moon. LRO's diviner instrument can also measure temperature, revealing the extreme cold within the craters. Finally, LRO's LEND instrument can measure the speed of neutrons to detect elements like hydrogen in the lunar soil. So, while there are some areas on the moon that never see the light of day, LRO will keep collecting data so that we can learn more about them. And as we continue to study the moon, we'll improve our understanding of Earth's original satellite and, pun fully intended, bring new discoveries to light.
That again was courtesy of the Science Visualization Studio. And I do want to point out again on those permanently shadowed regions, they are always in shadow, but they're not totally dark. You know, as they showed a bit of in the video, there is some starlight and there is some indirect lighting from, from reflections off crater walls and the surrounding areas. So it's more like if you were in like a decently big, if you're in like a decently big conference room and you drop the lights for a presentation, it's more like that level of light that what we'll be looking at there.
As you watch the moon over the course of a month, you'll notice that
the moon's south pole is a fascinating region to study, especially when you pay attention to the areas that are in sunlight and darkness over time. And thanks to NASA's Lunar Reconnaissance Orbiter, we can zoom in for an extremely close view of the terrain that shows how the sun shines on the South Pole. Here, we see how the moon's topography creates areas of shadows over the course of 2 lunar days, which is equal to 2 months on Earth. The flowing dance of sunlight and shadow on the surface reveals areas that exist in permanent darkness, nearly persistent sunshine, and others where the balance of light and dark fluctuates through time. Studying the shadows at the South Pole informs scientists about the temperature at and below the surface, and the possibilities regarding water and other volatiles, all of which sheds light on what future lunar exploration will entail. The moon's south pole is a
So I can say, yes, as far as that illumination mapping goes, actually, a couple of the people I work with do a lot of that for purposes of planning landings, because you want to make sure that you are landing in light. Which of course will depend on exactly when you land, but you need to land in light, and you also need to do it, at least for now, until there are any communication relays. You also want to land someplace that has a direct line of sight to Earth. So there's a lot of that that's going into the planning for potential traverses, along with challenges of the terrain, not wanting to go on particularly large slopes, all of that. But this kind of illumination from the topographic maps is really important. So here's just, here's just an example, just a still image here. This kind of putting everything together so that what you're seeing is the brightest areas correspond to being lighted about 80% of the time. And then there are a couple of permanently shadowed regions there that show up as being completely blank. So again, this is what happens when you can put together you can put together this much topography and have access to awesome computers. So now this is looking at the area where I showed the topography from Lola before, from that contour map. And what I have up here now, this is the temperature map from the Diviner thermal sensor. And so you can see, the very cold areas are in blue, and those pink outlines where we think the permanently shadowed regions are. And the thing is, the very coldest areas, what we're hoping for actually is you need the temperature to be hopefully below 125 Kelvin, which is about minus 235 Fahrenheit, in order to get stable ice. Because what you're looking at, in those vacuum conditions is the water ice very easily sublimes, just solid straight to gas state, like what dry ice does. So I think right now that there's just lots of little tiny ice crystals, and it's all mixed in with the regolith, which is the fancy name for the dust, and all the little broken up rocks mixed together. So based on temperature and lighting, here are some of those areas where potentially there could be water. And then this is going back to, so this is the lens, the neutron detector experiment that was mentioned briefly in one of the videos. So what goes on with this is that the moon's surface is constantly getting nailed with galactic cosmic radiation. So one of the things you can learn from studying the moon is that having a global magnetic field in an atmosphere is very good. Because otherwise, you are going to be constantly getting small meteors coming through, smacking into you, all kinds of nasty radiation, which again is part of the mission planning. But this particular cave, cosmic rays coming in, smacking into the surface, tends to release neutrons, subatomic particles, and they fly off into space. But in areas where the surface has a lot of hydrogen, not as much gets out into space. So LEND winds up detecting hydrogen by finding, all these dark and purple areas, by finding areas where there's less neutrons, which means more hydrogen. So you can see how, right, this is a great approach with the, let's bring in everything on one satellite, is because you can do all of this stuff simultaneously, line it up, and get some great perspectives there. So that's pretty much what I say about water on the moon. But I just want to jump ahead to one weird feature, because this is a Stargazers club, so I want to show something you can actually see. So here's a video about, well, Reiner Gamma swirl, narrated by...
Some of the strangest but most beautiful features on the moon are lunar swirls. The most famous one, Reiner Gamma, is a favorite target of backyard telescopes. Using data from the Lunar Reconnaissance orbiter, we now know swirls are the result of local magnetic fields in the moon's crust that act like stencils, selectively blocking radiation from the sun and causing parts of the surface to weather at different rates, producing interesting patterns and coloration.
Okay, so again, that further reinforces what I said about, having a global magnetic field is good on the surface if you don't want to be constantly smacked with things. And so I just want to show where, again, where you find minor gamma on the moon. So, near side, of course, all the way over on the edge here. There are some coordinates and a nice blow up. And then I want to note this image that I got, that the image not to scale does actually apply to the big image. But since I put an image of myself there, it is even more true for that one. So here I am at the Lunar and Planetary Science Conference earlier this year in Houston. And every year the Lunar and Planetary Institute has this big inflatable moon. This like super detailed, and it's like one of the spots where you get together and take, everybody gets photos. And so here I am pointing at it. So you can see from this angle, we're kind of looking sort of half at the far side on the left and half on the near side at the right. So, off to the right of the photos where the Earth would be, there was not an inflatable Earth, but if there were, that would be where you would put it. And so, since I happen to be currently studying that area, actually just submitted a paper about it, thought I would try finding it on the globe. And because my wife loves photos of me and I'm a dork, here I am. Here I am pointing that out. And again, here's another broader view of this. So you can see, right, this thing is huge. There's this central eye or heart region there. This is the biggest area that has those dark strips that actually aren't part of this world. So what was said in the last video is one of the leading hypotheses for how that happens. But this, like everything else, is up for study. So one of the possibilities is that because there is actually a local magnetic field here, that's steering the solar wind, which is basically a big bunch of radiation and charged particles. Well, magnetic fields move charged particles, so possibly it's moving them away from that area, and that'll leave it lighter because the combination being hit by the solar wind and radiation and being hit by, very small meteoroids is that there's a bit of melting and you wind up with like microscopic little blobs of pure iron, and those are really dark. So that's why anything on the moon, any areas of regolith, if it's been exposed for a long time, it gets darker, and you can tell how long it's been on the surface from that. So that's one way this could have happened. And then, another thing is, well, again, as the result of all the radiation coming in, there's a lot of static electricity at the surface of the moon. And again, some of the, dust particles are fine enough to be microscopic. So it's also possible some of this dust that just got levitated by just a little bit above the ground by the static electricity, maybe that also got steered by the magnetic field. And most of that dust is bright, so maybe that makes it. Another one, which I don't know, my recent research doesn't really support, but there's a possibility also that there was, these swirls result from there being a big comet impact, sort of scour the surface, flatten things out, mess things up, compacted things, and that's why it's brighter. So then, the sort of the two main things we want to know to try to figure out what happened are, one thing is, are the rocks in the light area, are they different from the rocks around there? Are they made of something else? They have more or less iron, something like that. Or maybe it's just that the surface is rougher or smoother, more compact, and and that's going to make it look different. And so we're looking forward to, hopefully in the next few years, on one of the next private missions, there's the Lunar Vertex lander and rover, which is out of Johns Hopkins Applied Physics Lab, just over in Laurel. And the idea is that combination is, they'll have magnetic field sensors, they'll have really detailed cameras to get the texture, and they'll have really good spectroscopes that can get at what elements and what minerals are in there. So if this mission succeeds, which would be awesome, and I know a bunch of the people who are working on this, it's a decent chance that that as close as we can get in science could be a definitive answer to settle all of the disputes among those of us who are just looking down at it. And so that's what I have. I just put it. Let's leave you with those couple of links. I got some of the images and videos that I showed from these sites, and there is an absolutely amazing amount of cool information if you want to go on these. So much outreach. So much outreach stuff, so many non-technical, semi-technical explanations, images, videos, awesome stuff from the visualization studio. And just last slide to wrap it up again, since this is Stargazers meeting, there is the International Observe the Moon Night coming up apparently this year on October 4th. And part of this, is signing up, organizing watch parties, putting things on YouTube, doing learning activities, and things like that. So I'm just put the hashtag up here, if this club is interested in doing that. And if you guys are contacting me, I'll help. And then I just kind of sneak my email address on there too. So if anybody wants to hear any more about this, I will happily blab for as long as possible. So I guess for a few minutes, if anybody wants to ask me anything else, hopefully restricted to things I actually know. Sure.
Is what was the importance of the law that we looked at? Is that where the next landing will be? And my second question is, if we have access to the hydrogen, how will you get the oxygen so that you can breathe out there?
Okay, so that's two questions just for, I would just try to say them again loudly for Zoom. So the question, one of them is the Reiner Gamma swirl, the huge blob about, is that possibly a future landing site? So it's not planned as a human landing site for Artemis, but that mission with the mission with the cute little rover, the Lunar Vertex thing, that's going to land there and take all the measurements. And okay, what was the second question? Okay, so most of the minerals that are on the moon are some kind of silicates, and they have oxygen atoms in there. And so what they're detecting are not necessarily lens. So with the neutrons, they're not necessarily, they detect hydrogen, but it's not necessarily going to be pure hydrogen. A lot of it is probably what's called hydroxyl, which is 1H, it's just HO. So there is going to have to be likely, some sort of process, other than just finding water ice directly. There'll probably also need to be development of some sort of, industrial type process to make water out of some of those things, and also get oxygen out of some of the rocks.
Okay, I think we're going to have to wrap it up. Let's have another round of applause.